G'day, in this video we're going to start to look at friction in a lot more detail and expand on what you would already know from junior topics. In particular, we're going to be distinguishing between static and dynamic friction. So in this video, we're going to be covering dot point 2.2.1, still in Module 2 Dynamics, and starting a new inquiry question which asks, how can the motion of objects be explained and analysed? So when explaining why objects move in the way that they do, friction is going to be a really big part of that because it's going to explain why objects do not move as much or begin to slow down instead of following Newton's first law. And the content statement, which covers friction in a lot of detail, is the first one, which is applying Newton's first two laws of motion to a variety of everyday situations, including both static and dynamic examples, the major focus for this lesson, and include the role played by friction by reflecting on the equation there, which is that the force of friction is equal to mu, which is a coefficient of friction, multiplied by the normal force. And we're going to be unpacking that equation today. So our key learning intentions is to first off be able to distinguish between static and dynamic frictions, and then also use friction coefficients to calculate the amount of force required to move an object to begin with, as well as the friction experienced by moving objects. And that's going to give us the capacity to begin to look at how we can include friction in dynamics calculations, enabling us to find net force. So first off, let's just get the basics done and actually reflect on what our definition of friction is. Essentially, it's a force which resists motion. And a lot of the time we talk about this idea or concept of rubbing between surfaces and matter, converting kinetic energy into sound and heat. A basic way of being able to conceptualize or visualize this concept is looking really closely at how two surfaces actually appear at a zoomed in level and appreciating that even for really smooth objects, there are bumps and crevices that exist on the surface of all solid objects. We do also see friction through fluid substances such as liquids and gases. We don't necessarily visualize the passing over of those bumps and ridges in the same way, but what we should be able to appreciate is that a solid object moving through a fluid is going to experience friction simply because it has to move past the fluid matter itself. So first off, when we talk about static friction, this is the friction that simply resists motion and keeps objects stationary. So in both of these examples, both people are not able to move their respective objects because static friction is essentially too much. There is an interacting resisting force which exists between the object that is being pushed and the surface below. Essentially, for this static friction force to be overcome, more force would need to be applied. Now, once that motion has been overcome, we start to look at something called dynamic friction. This doesn't stop objects from moving entirely like static friction does, but rather it is a resistance to motion of objects that are already moving, which will either mean that force will be applied to try and keep the object moving, or the object will inevitably slow down. We have three different subcategories: kinetic, rolling, and fluid. The example here of kinetic friction that exists is between the boxes, and the rubbing between solid surfaces here is characteristic of what we would define as kinetic friction. We also have rolling friction in this example. There is the rolling of the wheels. There is still friction that exists, but it doesn't work in exactly the same way as kinetic friction because the wheels are continuously turning. Technically as well, there is some kinetic friction between the floor and the clothing of the child that is riding on that trolley. We also have fluid friction, which exists again between liquids and gases. Parachuting is a fantastic example of friction that is existing between the air and the parachute itself. Essentially, this module is mostly going to be focusing on kinetic friction. And when we do a lot of our analysis, it is going to be focused on two solid objects rubbing against each other. So when we look at friction, we can refer back to and talk about Newton's first and second law to see how they actually fit together. When looking at static friction and first law, some comments that we can make is that friction, essentially static friction, resists change in motion, and that static friction must be overcome by a force before movement will occur. So we already know that according to first law, when an object is at rest, it remains at rest until something actually tries to move it. On top of that, if there is static friction involved, then that must be overcome before the object will actually begin to move. When we're looking at dynamic friction, this friction will stop motion at a constant velocity. So what we already know is that objects in motion remain in motion with the same speed and direction, essentially the same velocity, unless there is a force that changes it. Friction on Earth is pretty much always there, whether the object is moving through the air, moving through a liquid, moving across a solid, or some combination of both, there's also always going to be some degree of friction there. And that effectively is what stops this aspect of Newton's first law actually proving to be true in the context of moving objects on Earth. So what needs to happen to counterbalance that to try and maintain constant motion is some sort of force that directly counters the force of dynamic friction. When we look at second law, something that we can say is that the amount of force required for both static and dynamic situations will always depend on the mass of the object. We know that F is equal to ma, so the force applied is equal to the mass times the acceleration. Effectively, if there is more mass, we're going to need more. Essentially here, if there's more mass, it's actually going to press into the solid surface a little bit more. And that's going to mean that more force is required to overcome that force of friction. That will make a little bit more sense quite shortly. So when comparing static and dynamic friction, something that's really important to always keep in mind is that it's easier to push something which is already moving. And the reason for that is that the maximum static friction that an object can have is actually higher than the kinetic friction of an object. And to explain this, we can reflect on the concepts that are introduced in Newton's third law. So if I have a surface and some sort of object that's sitting on it that's about to get pushed, and I apply a force onto the box or the object. Now the force of friction will be equal and opposite, meaning that if I was to push with greater force, the force of friction will increase at the same rate. And that's being shown in the graph here. As you push and push and push on an object that's not moving yet with more and more force, the amount of friction that's resisting is going to be equal and opposite in the other direction. So we increase applied force. That means that there's going to be an equal amount of friction force until we hit this maximum point, the cap, I guess, on static friction. So we get to this maximum point, static friction won't be able to build up any further, which means that any additional force that we begin to apply will lead to motion. Once the body is moving though, kinetic friction is actually a little bit less than the original static friction that we had at the beginning. And this is something that we will unpack a little bit more in class. From a mathematical perspective, something that I want to introduce in this video is the idea of friction coefficients. And you will see that they are characterized with the Greek letter mu, which can be written mu. The Greek letter mu represents a coefficient for the friction between two objects. Essentially, this number gets greater if there is more friction that exists between the two objects. You'll notice that I've put down a mu s and a mu k, one for static friction and one for kinetic friction. In other words, the sliding of two solid objects or two solid surfaces against each other. And these coefficients will be different because, as we said before, the maximum static friction is going to be different to the actual kinetic friction when the object is being slid. But they are calculated in the same way. Essentially, the friction force between object A and object B is going to be equal to the friction coefficient times the normal force. So in a bit of a diagrammatic sense, what we could have is, again, an object, let's say that it's A, rubbing across a surface, let's just call that surface B. If we were pushing that object, say, toward the right, so an applied force, there will be some amount of friction which will oppose it. And that there would be our friction force that exists between A and B. What we will also have is the normal force and Fg as well, the force due to gravity, and these two forces will be equal and opposite to each other. But this normal force that's here is the normal force described in our formula up the top, the normal force between A and B. If you're using the static friction coefficient, then effectively when you go through this calculation and you sub in the static friction coefficient and the normal force, you're able to calculate the maximum frictional force of the stationary object. So essentially, how much applied force can you keep pushing until you hit that break point where motion's going to start? If you use the kinetic friction coefficient and substitute that in, what you'll be calculating is a frictional force on an object as it's actually sliding across the surface. And as I noted before, these two friction coefficients will be different, which means that static friction and kinetic friction will be different from each other as well. And what we should always get is static friction being larger than kinetic friction. And this is exemplified in a data table that looks like this. We should see here that the static friction coefficient is always greater than the kinetic friction coefficient, which means if you substitute in a static coefficient that's always greater than the kinetic, you're going to end up calculating a higher friction force than if you were to substitute in a kinetic one. Please note with this kind of data, the formulas themselves are not in the data sheet. It's something that we're going to have to practice and sort of build our capacity just to be able to do without the support of the data sheet. And you don't have to ever remember any of these static coefficients. In questions, they'll either provide you the data or they may ask you to calculate it based on other data given. To finish this video off, I want to apply some of these concepts around friction and friction coefficients by completing a simple calculation. So let's get over to the whiteboard. So in this question, we're being told that we have a 2 kilo box being pushed across the table. The coefficient of static friction between the box and the table is 0.5, and the coefficient of kinetic friction between the box and the table is 0.35. What we need to do first is calculate the maximum static friction of the box and the table. And then in part B, we need to try and figure out the frictional force as well as describe the motion of the box if it's being pushed with the following amounts of forces, so 5, 10, and 15 newtons. What I'm going to do first is draw up a diagram and start to pull out a lot of the data that we'll be working with for this question. So some key elements for this question. In part B, we've got a bunch of applied forces that we're going to apply, 5, 10, and 15 newtons. I've just drawn them to the right. Direction wasn't specified. What that's going to mean is that friction is going to go in the left direction. We can assume, based on how the question is written, that in some situations, friction is going to be static, and in some situations, friction is going to be dynamic. What we're probably going to need to figure out first is what is the maximum amount of static friction that can be had between the box and the surface. And to do that, we're going to need the normal force because that is a part of the equation for calculating static and kinetic friction. Essentially, the force of static friction is equal to mu s times the normal. And the force of kinetic friction is equal to mu k times the normal force. So the normal force is going to be quite important in this situation. And we always know that the normal force is equal and opposite inside to Fg, which we can calculate as mg, g being the acceleration due to gravity, or essentially 9.8. And I've just written that up here on the side in a bit of an algebraic way. Also recorded all of the data here in our data column. So I've got the value for mu s, mu k, and then the applied forces in 3 different scenarios. So for part A, what we're being asked to calculate is the maximum static friction of the box on the table, which means we need to find SF. And we've already written up an equation that fits with that. To find the static friction, we need to multiply together the coefficient of static friction by the normal force. Now we've been given the coefficient of static friction, it's 0.5. Fn we don't have though yet, however we can calculate it by multiplying it by mg. So that means we can find the force of static friction by multiplying again mu s, but not by Fn. Instead I'm going to substitute in mg here. So mu s is 0.5, that's the coefficient of static friction. The mass is 2, and g is equal to 9.8. When we multiply all of that together, we end up with a force for static friction, which is equal to 9.8 newtons. Effectively, what this means is if the applied force is 9.8 newtons or below, it's not going to be able to overcome the force of static friction, meaning that the box will not move. So let's see how that's going to apply to our questions in part B. So for this question, we need to analyze a bunch of different applied forces. We're going to look at the first one to begin with, and The applied force there is 5 newtons. So here for the first applied force, we can conclude that because the first applied force is definitely less than the maximum static friction, that the force of static friction in this case is going to be 5 newtons to the left. And we know that because the static friction is going to essentially match the applied force here. And we know that's going to be the case according to Newton's third law, which says that those two forces are going to be equal in magnitude but opposite in direction. Continuing on with B, the next applied force is going to be 10 newtons in size. So let's have a look at what's going to happen in that scenario. In this case, because the applied force is greater than the maximum static friction force, it means that first off, the box is going to move, and we're in a scenario where we're going to do a calculation for kinetic friction. And when we calculate for kinetic friction, all we need to do is multiply mu k by Fn. In this case, the coefficient of kinetic friction is going to be 0.35, and the normal force is going to essentially be calculated the same, 2 kilos times the acceleration due to gravity, which is mg. In this scenario, that means that the friction force is going to be 6.86 newtons to the left, which means it's going to be opposing the applied force. To then describe the motion of the object, we can calculate the net force and then apply the F equals ma equation to determine how much it's going to accelerate to the right. So just to summarize this solution, to calculate the net force, I just needed to add together the two opposing forces. So 10 newtons in the right direction, that's the applied force, and then 6.86 newtons of force in the opposite direction, giving me a net force of 3.14 newtons. All I then had to do was essentially substitute that number in with the mass of 2 kilos into the F equals ma equation, making sure that I had acceleration as my subject. And that's giving me the data here at the bottom to be able to describe the motion of the object when the 10 newtons of force is applied, effectively meaning that there's going to be an acceleration to the right of 1.57 meters per second squared. We should be able to appreciate that when we calculate for the 15 newtons of force, the solution should be very similar to the one that we just completed for applied force 2, and that's going to be because the 15 newtons of force are greater than the static friction. The only major difference is going to be that the net force is going to be different because the applied force is greater in that circumstance, meaning that there's also going to be a larger acceleration. It should be noted that for both of these scenarios, the kinetic friction that is opposing the applied force is going to be the same. And that's simply because this friction constant here is based on the interaction between the box and the table. It has nothing to do with the applied force. The mass that's being substituted in is constant as well, and so is the acceleration due to gravity. So in this question that I'm about to work with, when I calculate for 15 newtons worth of force, I will still be using this same kinetic friction force, meaning that I can skip that step effectively. So in summary for this question, we were able to use the coefficient of static friction first to determine what the maximum amount of static friction was going to be for this scenario, and that was 9.8 newtons. We were then able to compare the number of newtons of each applied force to that maximum force of static friction to see whether or not the applied force would overcome it. In the situation where it didn't, we were able to conclude here that there was no motion. Instead, we were able to make a comment that outlined essentially the size of the static friction force, and that was going to be equal and opposite to the applied force that was given. For the other questions, though, the applied force was greater than the maximum static friction, meaning that we had a kinetic friction problem, and it was going to oppose the applied force, and the remaining or net force was going to lead to an acceleration. In the first example, we found that that was 1.57 meters per second squared. And I said that it was simply to the right because there was no direction given in the problem. So I just followed what I'd drawn up in my diagram. And for the other, because the force was greater, according to Newton's second law, that should mean that we end up with a greater acceleration. And that's what we got there at the end. Just for consistency, I will also note that this is to the right. Thank you very much. In the next video, we're going to be looking at applying kinematics concepts to Newton's second law of motion. Already, I began to do that in the inclined plane video a couple of videos ago. The practice question that I'm going to be running through here in this example is going to be quite similar, but is going to reinforce the idea that Newton's second law of motion, generally speaking, is our bridge between kinematics and dynamics, as that law contains both force and acceleration. Force being a dynamics measurement, and acceleration being a kinematics measurement. And in that question, unlike the first solution that I gave you for motion on an inclined plane, we're going to begin to introduce the concept of friction to that solution. I'll see you on the next one.